Now, picture this. The horizon above the Kansas prairie is warping in a blinding, shimmering haze. The topsoil has baked into a rigid grid of cracked, gray clay, hot enough to scorch leather boots through the soles. On the surface, ambient air temperatures have breached 118 degrees Fahrenheit. The regional electrical grid, overwhelmed by millions of central air conditioners humming at maximum capacity, has finally snapped. High-voltage transformers along the county line are failing, popping one by one under the sheer thermal load. Modern suburban living rooms across 3 counties are transforming into suffocating glass and drywall ovens within hours. And yet, down here, absolute silence. Step down a narrow, subterranean concrete stairwell, past a heavy, airtight pressure door, and the deafening roar of the prairie cicadas cuts out instantly. The air suddenly tastes clean, heavy, and crisp. If you turn off your flashlight, you are enveloped in a total, velvety pitch-black darkness. Exhale slowly, and you can actually see the faint plume of your own condensed breath hanging in the beam of a thermal imaging camera. The sensor reading on the solid earth walls isn't 90 degrees. It isn't even 70. The digital display flatlines at precisely 55.4 degrees Fahrenheit, without a single solar panel, without a generator, without a single watt of grid electricity. A family is sleeping beneath thick wool blankets in the middle of the most destructive summer heat wave on record. Think about that for a second. When every neighbor's central air conditioner died, leaving them trapped in a blistering furnace, this shelter maintained a natural temperature cooler than a commercial refrigerator's beverage display. Most people assume that if you want to escape summer heat by going underground, you just grab a shovel and start digging. But here's what everyone missed. If you dig 5 feet down, your shelter will warm up to 75 or 80 degrees by late August. If you dig 8 feet down, seasonal moisture and soil compression will turn your shelter into an 85-degree humid vapor bath. To tap into an infinite, passive thermodynamic cooling engine, you have to breach a very specific geological boundary. You have to go down precisely 15 feet. At 15 feet beneath the surface, something incredible happens to the laws of heat transfer. You cross beneath the atmospheric thermal wave. The dirt above your head ceases to act like ordinary dirt and transforms into a massive, slow-motion thermal battery operating on a 6-month delay. The scorching heat of July won't reach this subterranean depth until the dead of January. And the freezing cold of February won't penetrate down here until the middle of July. Let that sink in. This isn't an accident of luck. It is a precise empirical application of soil physics, hydrodynamics, and structural engineering. Over the next hour, we are going to audit every inch of this 15-foot subterranean structure. We will calculate the exact mathematics of soil thermal mass. Examine the dangerous structural mistakes that crush unwary builders. Unpack the deadly mechanics of atmospheric moisture control, and reveal the mandatory, life-saving ventilation engineering required to prevent an underground shelter from turning into a silent carbon monoxide trap. Subscribe to the channel right now and save this technical breakdown, because understanding how to survive total grid collapse using the timeless physics of the Earth itself is the ultimate blueprint for off-grid independence. Now, to understand why digging 15 feet down works so exceptionally well, we first have to examine why every traditional house built above ground is engineered to fail during an extreme heat crisis. The year was 1936, July, in the heart of the American Great Plains. A historic heat dome settled over North America, locking millions of acres in a vice grip of unyielding solar radiation. State after state shattered weather records that still stand today. In North Dakota, temperatures soared to 121 degrees Fahrenheit. In Kansas and Nebraska, day after day brought ambient shade readings of 115 degrees. Back then, there was no central air conditioning. There was no widespread electrical grid to pump cool air into bedrooms. Farm families watched their livestock collapse in the yards. Inside standard 2-story wooden farmhouses, top-floor bedrooms turned into fatal heat traps, reaching interior temperatures exceeding 130 degrees. Modern historians often focus on the dust storms, but the heat was the quiet killer. Thousands of people died in their own beds, overcome by physiological heat stress. The survivors, the homesteaders, who endured without modern technology, didn't survive by building thicker wooden walls. They survived because they abandoned the surface entirely. They retreated into shallow root cellars, dug out homes carved into riverbanks, and earth-sheltered basements. They discovered, through raw trial and error, that the dirt under their feet possessed a mysterious cooling power that no above-ground structure could ever match. Fast forward nearly a century. We like to believe our modern homes are vastly superior to those wooden 1930s farmhouses. We line our walls with pink fiberglass. We spray polyurethane foam into our attics. We install high-efficiency double-pane, low-emissivity glass windows. We wrap ourselves in high-tech materials and convince ourselves that high R values will protect us from the elements. The numbers don't lie. An R value, whether it is R13 in your walls or R38 in your attic, is merely a measure of thermal resistance. It dictates how slowly heat travels through a material. That's it. R value is not a barrier, it is a speed bump. Imagine your attic on a bright July afternoon. The sun beats down on black asphalt roof shingles with a radiant energy flux of roughly 1,000 watts per square meter. Within 2 hours, those asphalt shingles heat up to 160 degrees Fahrenheit. That immense heat conducts directly through the plywood roof decking and radiates down into your attic space. Your attic space quickly reaches 140 degrees Fahrenheit. Beneath that attic floor sits your ceiling insulation, that proud R38 barrier you paid thousands of dollars to install. For the first 2 or 3 hours, the insulation does its job. It slows down the flow of heat, but heat flows down a thermal gradient continuously, seeking equilibrium. The higher temperature always moves toward the lower temperature. After 6 hours of continuous, unyielding 140-degree heat baking your attic, the fiberglass insulation reaches its maximum thermal saturation capacity. The speed bump breaks down. Heat begins pouring directly through the drywall and into your living space. Your 3-ton central air conditioner kicks on. It burns 3,500 watts of electricity every single hour just to pump that heat back outside. As long as the electrical grid is delivering 2,400 volts to your neighborhood transformer, your house stays at a comfortable 72 degrees. You feel safe. You feel in control. But modern power grids are fragile balancing acts. Electric motors under extreme heat draw vastly more current. As ambient temperatures rise toward 110 degrees across an entire state, millions of air conditioners run non-stop. The electrical grid experiences catastrophic demand spikes. Voltage sags, high voltage lines expand, sag into tree branches, and short out. Substations trip, and suddenly, in a fraction of a second, the hum stops. The air conditioning dies within 90 minutes. The cool air stored in your drywall and furniture is completely erased. The continuous radiant heat stored in your saturated roof and attic insulation surges downwards. Within 4 hours, your indoor air temperature breaches 90 degrees. Within 8 hours, it matches the surface heat outside. Within 24 hours, your sealed, double-pane glass home turns into a greenhouse. The air trapped inside becomes stagnant, humid, and dangerously hot. When the wet bulb temperature, the metric that combines ambient heat with relative humidity, crosses 95 degrees Fahrenheit, the human body loses its ability to cool itself through sweat evaporation. At that point, regardless of how much water you drink, regardless of whether you sit perfectly still in the dark, your internal core temperature begins to climb. Heat stroke becomes mathematically inevitable. Our modern homes are not fortresses. They are high-tech insulation boxes, completely dependent on an uninterrupted flow of grid electricity. The moment that energy flow stops, the thermal trap springs shut. This brings us back to the crucial question. Why did the homesteaders' earth-sheltered dugouts work when their wooden houses failed? And why did digging down to 15 feet create an unshakable oasis of cool air while surface homes baked? To answer that, we have to throw out the concept of R-value insulation and step into the extraordinary physical reality of thermal mass and geological time lag. If you take a heavy-duty hydraulic excavator out into an open field in midsummer and drop the bucket into the ground, the first 3 feet of excavation feel like breaking through dried brick. The topsoil is hot, dry, and bleached pale by months of merciless sun. As the steel teeth of the bucket bite 5 feet deep, the character of the earth changes. The soil grows darker, heavier, and noticeably cooler to the touch. But 5 feet down is a dangerous illusion. Here's what everyone missed. If you stop digging at 5 feet and build a buried shelter, you haven't escaped the reach of the sun. At 5 feet deep, soil temperatures still swing by 25 to 30 degrees throughout the year. The summer heat wave baking the surface will slowly seep down to your ceiling by late August, driving the interior temperature up into the high 70s or low 80s. Worse still, at 5 feet, soil is highly susceptible to frost heave in winter and severe moisture infiltration during spring rainstorms. To reach absolute thermodynamic stability, the machine must keep digging. By 8 feet down, the diesel engine of the excavator works harder. You hit dense, tightly compacted subsoil clay and gravel. Here, the ambient ground temperature drops closer to 60 degrees. But 8 feet down presents a catastrophic engineering hazard that has killed countless untrained off-grid builders: trench collapse. A single cubic yard of moist clay, or packed dirt, weighs between 2,700 and 3,200 pounds. That is more than 1.5 tons of loose earth per cubic yard. When you cut a straight vertical bank 8 or 10 feet deep without proper structural support, the lateral earth pressure builds silently. Soil does not give you a polite warning before it fails. It doesn't creak or groan like wood. A vertical earth wall shear fails in a split second. Thousands of pounds of suffocating clay slide downward at 30 miles per hour, trapping anyone in the pit beneath 4 tons of crushing weight. The sheer pressure on a human chest at that depth makes it physically impossible to expand your lungs. Professional subterranean engineering requires rigid safety standards. You must cut the soil using stepped benching or slope the trench walls back at a precise 45-degree angle of repose, widening the surface footprint of the excavation significantly to prevent shear failure before a single concrete wall is poured. As the excavation bucket reaches 12, 13, 14, and finally 15 feet down, you step into a completely different geological realm. At 15 feet down, the surface world disappears. The blinding glare of the summer sun is replaced by deep shadow. The scorching heat is completely gone. If you press your bare palm against the deep clay wall at 15 feet, it feels as cool and damp as a slab of polished marble pulled from an ice house. You have reached the Earth's permanent thermal equator. At 15 feet below grade across most of the continental United States, ground temperature ceases to track daily or monthly weather patterns. The daily solar flux that warms the surface during the afternoon cannot penetrate this deep. The annual temperature variation at 15 feet compresses down to less than 2 degrees Fahrenheit year-round, holding steady at the region's exact mean annual air temperature, 55.4 degrees Fahrenheit. Now, picture this. You stand at the bottom of a 15-foot deep stepped excavation pit. The air around your boots is 55 degrees, while 15 feet directly above your head, the topsoil surface is baking at 115 degrees. You are standing inside a natural thermodynamic reservoir that has remained untouched for thousands of years. But carving a 15-foot pit is only 10% of the battle. The real engineering challenge begins when you attempt to build a permanent structure that can survive inside the earth without being crushed, flooded, or suffocated. The first dynamic you must engineer against is hydrostatic and lateral earth pressure. Soil is not a static block. It is a dynamic, fluid mass that expands and contracts with moisture. At a depth of 15 feet, the lateral pressure pushing inward against your shelter walls is immense, averaging roughly 100 pounds per square foot for every foot of depth. That means near the floor of a 15-foot subterranean room. Every single linear foot of wall is enduring 1,500 pounds of continuous, inward-pushing pressure. If you attempt to construct subterranean walls using unreinforced cinder blocks or thin timber framing, that lateral earth pressure will buckle the center of the walls inward, like an aluminum soda can within months. To survive 15 feet underground, subterranean walls must be constructed from steel, reinforced, solid poured concrete. The structural blueprint requires an 8-inch to 12-inch thick monolithic pour, tied together with a dense grid of number 4 grade 60 steel rebar, spaced every 12 inches on center, vertically and horizontally. The footings must be poured directly onto undisturbed, compacted subgrade soil, engineered to transfer the immense dead load of the structure and the overhead soil burden evenly into the deep earth. Once the concrete forms are stripped, you face the second great enemy of subterranean engineering: water. Groundwater is relentless. Gravity forces rainwater down through topsoil until it hits impermeable clay layers or the deep water table. At 15 feet down, water surrounding your structure exerts hydrostatic pressure. It will find every microscopic hairline crack in concrete, every cold joint where wall meets footing, and force its way inside under continuous pressure. Building a dry subterranean shelter requires a multi-layered, redundant waterproofing system. First, the raw exterior concrete walls are coated with a thick elastomeric asphaltic emulsion, a rubberized liquid membrane that cures into a seamless, flexible waterproof skin capable of bridging small concrete expansion cracks. Over this elastomeric layer, you apply high-density dimpled drain board. The dimples create an uninterrupted air gap against the wall, allowing any water seeping through the soil to drop harmlessly down to the footings by gravity rather than pressing against the concrete. At the base of the footings, completely surrounding the structure, sits a heavy-duty perimeter French drain system. This consists of a 4-inch perforated rigid polyvinyl chloride pipe laid inside a bed of washed crushed stone, wrapped in high-flow geotextile filter fabric to prevent silt clogging. Any groundwater reaching the foundation is immediately collected by the French drain and directed by gravity to a dedicated gravel drainage basin far away from the shelter. Finally, before backfilling the excavation, a thick blanket of sodium bentonite clay paneling is placed against the drain board. Sodium bentonite is a natural volcanic clay that expands to 15 times its dry volume when exposed to water. If groundwater ever manages to penetrate the outer layers, the bentonite clay hydrates, swells into an impenetrable, self-healing gel barrier, and locks the water out permanently. And now, we encounter the single most common design flaw made by amateur off-grid builders. A mistake that completely ruins the natural earth cooling effect. The insulation trap. When people build an underground house, their instinct, trained by above-ground construction codes, is to line the exterior concrete walls with rigid foam board insulation. Think about that for a second. If you place 3 inches of rigid foam insulation between your subterranean concrete wall and the cool earth, you have effectively severed the building from its thermodynamic heat sink. You have insulated the house from times the 55-degree dirt, inside a heavily insulated underground room. Human body heat, light bulbs, cooking appliances, and electronic gear generate internal thermal loads. Because the wall insulation prevents that internal heat from transferring outward into the 55-degree clay, the heat gets trapped inside the room. Within 3 days of continuous occupation, your underground sanctuary warms up to 80 degrees, relying once again on electrical air conditioning to stay cool. To build a true passive subterranean cooling engine, the concrete walls must remain in direct, uninsulated thermal contact with the waterproofed subterranean earth. The high thermal density of the concrete acts as a thermal bridge, conducting heat rapidly out of the room air and absorbing it into the infinite heat sink of the 15-foot soil mass. The concrete wall doesn't just block earth, it becomes part of the earth. But once you establish direct thermal contact with 55-degree soil, you trigger a massive, complex, physical phenomenon that can destroy your indoor air quality in less than 48 hours. The dew point condensation crisis. When hot, humid summer air from the surface, say 95 degrees Fahrenheit with 70% relative humidity, is drawn down into a subterranean room whose concrete walls are sitting at 55 degrees. The laws of psychrometrics dictate an immediate atmospheric reaction. Air at 95 degrees can hold a massive amount of invisible water vapor. But as that warm air travels down into the 15-foot shelter, its temperature rapidly drops. As air cools, its capacity to hold water vapor shrinks dramatically. The relative humidity of the air climbs closer and closer to 100%. When that 95-degree air touches the 55-degree concrete wall, it instantly drops below its dew point temperature. The invisible water vapor in the air condenses in real time. Thousands of tiny water droplets form on the concrete walls, ceiling, and floor. Within 24 hours, an unengineered subterranean shelter will be dripping wet. Puddles will collect on the floor, and toxic black mold spores will begin rapidly colonizing every wooden surface, mattress, and piece of clothing inside the space. This is why traditional root cellars often smell damp and musty. They are drowning in their own condensation. Solving the dew point crisis without using electricity requires a brilliant application of passive thermodynamic fluid mechanics, earth-air heat exchangers, and passive solar chimneys. Instead of pulling hot, humid surface air directly through a door or simple window vent, the intake air must be routed through a network of long, smooth-walled underground pipes buried at a depth of 10 to 12 feet, known as earth tubes. As warm surface air is drawn through a 200-foot loop of underground intake pipe, the surrounding 55-degree soil slowly pre-cools the air times before times it ever reaches the living space. Because this pre-cooling happens inside the sealed earth tubes, the moisture in the air condenses, times inside, times the tubes, draining harmlessly away into an engineered low-point condensation sump installed beneath the ground outside. By the time the surface air finally enters the subterranean living chamber, it has already been cooled to 60 degrees, and its excess moisture has been physically stripped away. The air enters the shelter crisp, dry, and cool. To drive this continuous airflow without an electric fan, you employ a solar chimney, a passive thermal siphon. A solar chimney is a black, heat-absorbent vertical duct mounted on the surface above the shelter, facing due south. As the sun beats down on the black solar chimney, the air inside it heats up to 140 degrees or higher. Because hot air is lighter and less dense than cool air, it rushes rapidly upward out of the top of the chimney by natural buoyancy. This powerful upward draft creates a continuous low-pressure vacuum inside the subterranean shelter, which naturally pulls fresh, cool, dehumidified air through the buried earth tubes and into the living space. The hotter the sun bakes the surface, the faster the solar chimney heats up, and the faster, cool, fresh air is drawn through your 15-foot deep sanctuary. Nature powers its own air conditioning system. The numbers don't lie. A properly engineered passive earth tube and solar chimney system can exchange the entire air volume of a 15-foot subterranean shelter every 2 hours, keeping relative humidity safely below 50%, maintaining a steady temperature of 56 degrees, and using exactly 0 watts of electrical power. However, as magnificent as passive subterranean cooling is, moving off-grid into a subterranean space introduces a life-threatening hazard so dangerous, so silent, and so unforgiving that a single mistake in mechanical design will prove fatal. We are talking about carbon monoxide poisoning and atmospheric oxygen depletion. Let that sink in. In an above-ground house, wooden framing, drywall seams, window frames, and soffit vents create natural air leakage. Above-ground homes leak air constantly. A 15-foot subterranean shelter, constructed from solid poured concrete, wrapped in elastomeric membrane, and buried beneath thousands of pounds of clay, is a hermetically sealed pressure vessel. There are no drafts. There are no natural wall leaks. The air inside that room is entirely static unless you actively move it. If an off-grid survivor lights a small wood stove, a propane heater, a kerosene lamp, or even a simple candle inside an underground shelter without a dedicated combustion engineering system, an atmospheric catastrophe unfolds with terrifying speed. To understand why this is so deadly, we must analyze the molecular physics of carbon monoxide and oxygen displacement. When any carbon-based fuel burns, it consumes ambient oxygen molecules from the room and releases carbon dioxide, water vapor, and carbon monoxide. Carbon monoxide, chemical formula CO, has a molar mass of 28.01 grams per mole. Ambient atmospheric air, which is primarily nitrogen and oxygen, has an average molar mass of 28.96 grams per mole. This means that carbon monoxide has a relative density of 0.967, making it almost identical in weight to normal air. In a sealed subterranean space with stagnant air, carbon monoxide does not automatically rise to the ceiling like hot smoke, nor does it drop to the floor like heavy propane gas. It mixes completely and uniformly into the breathing air of the room. As a fire burns inside a sealed subterranean chamber, it consumes the available oxygen rapidly. Normal atmospheric air contains roughly 21% oxygen. When oxygen levels in a room drop below 19.5%, human cognitive function begins to degrade. You become slightly lethargic, your judgment grows hazy, and your reaction time slows down. As oxygen levels drop further, the combustion process inside your stove or heater degrades. Deprived of sufficient oxygen, fuel stops burning cleanly into carbon dioxide and begins producing massive quantities of toxic carbon monoxide gas. At a concentration of just 400 parts per million, 400 molecules of carbon monoxide for every million molecules of air. A human will experience severe frontal headaches, nausea, and dizziness within 1 to 2 hours. At 800 parts per million, carbon monoxide causes complete unconsciousness within 45 minutes and death within 2 hours. Because carbon monoxide is completely colorless, completely odorless, and completely tasteless, a sleeping family will never wake up. They simply drift from deep sleep into a fatal coma as the gas fills the room. This is why strict YMYL life safety engineering standards must be enforced in every subterranean structure. Here is the non-negotiable life safety specification for subterranean combustion and heating. Specification 1. Sealed combustion intake systems. Under no circumstances should any open flame heating appliance draw its combustion air from inside the subterranean living space. Every wood stove, furnace, or gas heater installed in an earth-sheltered structure must feature a sealed combustion chamber. A dedicated, airtight metal intake pipe must run directly from the exterior surface above ground, down through the soil, and connect directly to the firebox of the stove. The stove draws 100% of its air from the outside atmosphere, consuming zero oxygen from the underground living quarters. Specification 2. Insulated positive draft flue chimneys. The exhaust chimney from the stove must be constructed from double-walled, factory-insulated stainless steel pipe. It must extend vertically upward from the subterranean firebox, penetrating through the underground ceiling and rising at least 3 feet above the surface soil outside. The flue pipe must be fully insulated. Why? Because as hot exhaust gases travel up through cold subterranean ground, the gas cools down. If the exhaust gas cools too quickly inside an uninsulated flue pipe, it loses its thermal buoyancy. The upward draft collapses, creating a deadly backdraft that forces heavy carbon monoxide exhaust gases back down the chimney and straight into the living room. An insulated chimney pipe keeps the exhaust gases hot all the way to the top, maintaining a powerful, continuous upward suction draft that exhausts all toxic combustion gases safely above ground. Specification 3. Atmospheric exchange and redundant sensing. To prevent oxygen depletion from human respiration alone, every subterranean shelter must maintain a continuous fresh air ventilation exchange rate of at least 0.35 air changes per hour, or 15 cubic feet per minute per occupant. Furthermore, every subterranean sanctuary must be equipped with 2 independent, battery-powered carbon monoxide alarms. These detectors must be mounted at breathing height, approximately 5 feet from the floor, near the sleeping quarters. The alarms must be tested monthly and fitted with fresh lithium batteries every 12 months. When you engineer a subterranean structure with solid concrete retention, elastomeric waterproofing, earth tube dew point management, and sealed combustion atmospheric safety, you do not merely build a dugout. You build an indestructible, self-regulating thermodynamic fortress capable of keeping your family alive through the most extreme climatic catastrophes in human history. And to prove that, we are going to look at the empirical real-world sensor data from a 5-day heatwave grid failure test. Now, picture this. It is 2 o'clock on a Thursday afternoon in mid-July. A massive, high-pressure heat dome has stalled directly over the central United States, trapping a stagnant mass of superheated air across a 6-state region. On the surface, the weather station sensors are recording an ambient shade temperature of 118 degrees Fahrenheit. The sun burns through a cloudless, milky white sky, pummeling topsoil, asphalt, and rooftops with unrelenting radiant thermal energy. On the local suburban grid, disaster strikes. At 2:14 in the afternoon, 3 major regional transmission lines sag under extreme electrical resistance, contacting high-voltage grounding towers. A cascading trip sequence ripple through the regional energy market. Substation breakers slam open. In less than 3 seconds, electric power disappears across 35,000 square miles. Inside a standard 2-story suburban home 3 miles away, the hum of the central air conditioner instantly dies. The ceiling fans coast to a stop within 20 minutes. The radiant heat, trapped inside the attic rafters, begins pouring through the ceiling drywall. By 5 o'clock that evening, the indoor temperature inside that above-ground house reaches 94 degrees Fahrenheit, with 70% humidity. By midnight, it is a suffocating 98 degrees inside bedrooms. The family inside is sweating profusely, unable to sleep, watching their smartphone batteries drain while praying for the grid to return. Now, step across the property line and step down 15 feet into the subterranean shelter. Day 1, Hour 4 of the grid blackout. Outside, the ambient air is 118 degrees. Topsoil surface temperatures have spiked to an astounding 142 degrees Fahrenheit. Inside the subterranean chamber, there is no electricity. No backup generators are running. No batteries are discharging. A high-precision digital thermocouple mounted on the solid poured concrete wall reads exactly 55.4 degrees Fahrenheit. The air inside feels like a mountain cave in early May. The family sits at a wooden table, illuminated by a soft, low-voltage solar lantern. They are wearing light wool sweaters and long pants. While the neighbors on the surface are suffering in sweltering 95-degree indoor heat, the temperature down here hasn't moved a single tenth of a degree. Day 2, Hour 24 of the blackout. The heat wave on the surface intensifies. With zero wind, solar radiation continues to pump energy into the ground. On the surface, asphalt streets are softening into sticky tar. Car tires leave impressions in the melting pavement. 3 feet beneath the grass, ground temperature sensors show a sharp rise, climbing from 68 degrees up to 86.2 degrees Fahrenheit. The upper layers of Earth are absorbing the thermal wave, saturating with surface heat. At 10 feet down, the thermal wave slows down dramatically, registering a tiny nudge from 58 degrees up to 59.1 degrees. But at 15 feet down, inside the concrete living quarters, the temperature reading is completely flat, 55.4 degrees Fahrenheit. The sheer thermal mass of the 15-foot soil overburden, weighing hundreds of tons, absorbs the surface heat energy like a massive sponge, converting the high-intensity heat into an imperceptible microfractional temperature rise that won't actually manifest at this depth for another 6 months. Day 3, Hour 48 of the blackout. A new challenge emerges inside the shelter: the atmospheric humidity test. With 4 human beings living, breathing, and cooking inside a sealed concrete space, interior moisture levels begin to rise. The digital hygrometer on the wall ticks upward, climbing from 45% relative humidity to 68%, then 75%, then hitting a critical threshold of 82%. Microscopic droplets of condensation begin forming on the uninsulated steel door frame near the entry vestibule. The indoor air feels heavy. This is the exact moment where unengineered underground shelters fail, drowning in dampness and mold. The builder activates the passive solar chimney. On the surface, the black, heat-absorbing solar exhaust stack is sitting in full, direct sun, reaching an internal pipe temperature of 145 degrees Fahrenheit. The superheated air inside the vertical pipe rushes upward toward the sky, creating a powerful natural thermal siphon vacuum at the base of the stack. Underground, you can actually hear the reaction. A soft, steady whistle of air begins moving through the earth tube intake vents. Warm, moist air inside the shelter is pulled rapidly up and out through the solar chimney. Simultaneously, fresh exterior surface air is sucked down into the 200-foot underground earth tube loop, buried 12 feet deep in the dirt outside. As the hot 95-degree surface air travels through the cool underground pipe loop, its temperature drops to 58 degrees before it ever reaches the room. The excess moisture inside the air condenses safely times inside times the external drainage pipe, running off into a gravel sump outside. Within 3 hours of passive solar siphon operation, without using a single watt of electricity, the relative humidity inside the subterranean room plummets from 82% back down to a crisp, dry 48%. The air inside smells fresh, clean, and completely dry. Day 4. Hour 96 of the blackout. Surface conditions are reaching catastrophic levels. Emergency medical services are overwhelmed by heat stroke calls. Municipal water pressure is dropping as water treatment plants exhaust their backup diesel fuel supplies. Inside the subterranean shelter, the life safety atmosphere audit is conducted. A calibrated carbon monoxide analyzer is held at breathing height near the center of the living area. The digital display reads 0 parts per million. The sealed combustion intake pipe feeding the small cooking stove continues to draw its air directly from the outside, while the insulated vertical flue chimney exhausts all combustion gases high above the ground surface. Oxygen levels inside the room hold steady at 20.9%, perfectly matching natural, sea-level atmospheric air. The family cooks warm meals, drinks clean water, and sleeps peacefully through the night under flannel blankets. Day 5. Hour 120 of the blackout. The regional power grid remains completely dead. On the surface, modern suburban homes have reached interior equilibrium with the ambient air, hovering at 98 degrees during the day and 88 degrees at night. Food inside kitchen refrigerators has rotted. Living spaces are unlivable, down at 15 feet. The thermistor logs record the final verdict of the 5-day heatwave test. After 120 consecutive hours of absolute grid failure, during one of the most severe heat domes in regional history, the subterranean core temperature sensor reads 55.5 degrees Fahrenheit, a total temperature rise of exactly 0.1 degree. The numbers don't lie. Here is the empirical thermodynamic data from the multi-depth sensor array recorded during the climax heatwave audit. At the surface, ambient air temperature peaked at 118.4 degrees Fahrenheit. Topsoil surface temperature hit a blistering 142.1 degrees. Inside the attic space of the traditional above-ground house, temperatures peaked at 148.6 degrees Fahrenheit, creating a thermal driving force that overwhelmed R38 roof insulation within 6 hours. At a depth of 3 feet underground, shallow earth sensors recorded 86.2 degrees Fahrenheit, proving that shallow root cellars and shallow basements cannot offer true passive summer cooling during sustained heat waves. At a depth of 15 feet underground, deep Earth sensors flatlined at 55.4 degrees Fahrenheit, continuous baseline. To achieve that same degree of continuous cooling in an above-ground house during a 5-day heat wave, a standard central air conditioning system must consume roughly 150 kilowatt-hours of high-voltage grid electricity, generating hundreds of pounds of carbon emissions and relying entirely on a fragile utility grid. The 15-foot subterranean structure consumed precisely 0 kilowatt-hours. It didn't require repair. It didn't require mechanical maintenance. It didn't require fuel. It simply relied on the mathematical certainty of thermal inertia, the timeless physical reality that 15 feet of Earth absorbs radiant solar energy on a 6-month, 180-day phase delay. When surface homes are baking in the deadliest fires of summer, a 15-foot subterranean structure is still enjoying the deep, stored cold of the previous January. Think about that for a second. For over a century, modern architectural engineering has been obsessed with fighting nature. We build lightweight glass and wood boxes above ground, expose them to brutal weather extremes, and then install massive, noisy electrical machines to blast those boxes with hot or cold air to force them into temporary habitability. We spend billions of dollars every year maintaining an artificial environment that collapses the second a power line snaps in a storm. Subterranean engineering represents a fundamental shift in philosophy. Instead of fighting the laws of thermodynamics with brute force and continuous electrical energy, you step inside the laws of physics. You utilize the infinite thermal mass of the Earth beneath your feet to achieve permanent, passive thermodynamic equilibrium. You stop fighting nature and let the Earth protect you. However, as you plan your own journey toward off-grid survival and subterranean engineering, you must remember that the Earth is a powerful, unyielding force that demands absolute respect. Here is our mandatory life safety and engineering warning. Constructing a subterranean shelter is a complex structural and geological undertaking. You must never attempt a deep excavation without professional structural engineering approvals, soil stability analysis, and strict adherence to excavation safety regulations. A simple soil cave-in can be fatal in a fraction of a second. Furthermore, atmospheric ventilation, moisture management, and carbon monoxide prevention are non-negotiable life safety systems. Never operate an open flame, unvented fuel heater, or combustion generator inside any underground space. Always install redundant, battery-operated carbon monoxide detectors, ensure proper radon gas mitigation, and maintain engineered fresh air exchange systems at all times. When you respect the engineering, when you follow the physics, and when you build with reverence for the structural forces of the ground, you unlock the ultimate sanctuary, a place of absolute quiet, absolute safety, and permanent thermal comfort. 15 feet beneath a chaotic world.